Okay. So I'd like to thank everyone for being here, and it's a pleasure to address this meeting. This is a meeting that we had for a number of years, and it's very close to my heart. Let me make some general remarks. So the basic plan of my talk is actually I'll try to be very, very light, although the subject becomes tough very, very quickly. So I have a big outline, and you can see that the outline is long, but I'll promise I'll finish on time, hopefully. And I also like to say that the only thing that's in between you and vacations, at least from this conference, is my talk. So this is a further reason for being light. Okay. So I'd like to start actually with some general background on what we have been doing for many years, so that so many friends are here and some people have followed what we have done. So what we have is actually the work of a lab called Laboratory for Analysis and Mathematical Modeling in the Applied Sciences. This is a lab that I've been running with the help of students and colleagues from different universities, colleagues that are not based at IMPA, where we have tried to put together different areas of mathematics, energy, biosciences, physics, and trying to use these, different areas of science, I must say, applied sciences, that's part of the name, and we have been trying to use different areas of mathematics to attack those problems. So PDEs, numerical analysis, probability and statistics, optimization, inverse problems. So that's the vision we have for this lab, and I hope this is a project that interests many of you. I wanted to say some highlights of the last 10 years. We had, with non-governmental funding, especially Petrobras and Bovespa, we had about 13 postdocs, over 22 master science students, with the number growing, perhaps by the end of the year, 23. Long-term visitors, 2 special visitors. In particular, I'd like to mention the presence of Professor Moceni here, and who is one of those visitors I'm referring to, and Professor Uri Asher, who is one of the collaborators in the paper I'm going to describe very soon. We had, as I mentioned, several industrial projects and registered softwares. So this is a project that I hope that will keep on for the next few years. We also had, in such projects, the pleasure of having the contribution and collaboration of Shu Yang, who is hiding somewhere over there, and Yuri Saporito, and both of them are actually collaborators in the paper that I'm going to describe now. Okay, now, again, still in the subject of general context and general vision, this meeting that we have, about to finish in a few minutes, if I don't keep on talking forever, is actually part of a program, Parameter Identification in Mathematical Models. This is a program that started in October as a special thematic program of IMPA. And we started in October with new trends in parameter identification for mathematical models. And in a certain sense, my talk is totally along these lines, and I'll try to really emphasize that aspect. So let me start actually by reminding people what we mean by inverse problems. In fact, there is a general idea about different cultures, and this is one of the hopes I have here. Try to put together different communities many of the things that we talk about in inverse problems are things that people actually have been talking in statistics for many years, and I'm very glad that Professor Ulf Schmock gave the talk before me, because he showed you some aspects of theoretical statistics that actually touch very, very deeply analysis, for example, Wasserstein metrics and Kolmogorov metrics. And I'm going to talk from the perspective of analysis touching topics of statistics. So in inverse problems, we basically have models that give you data, usually noisy data. Such noise data is coming from parameters that go into the model. And usually from there, you try to also compute some quantity of interest. By the way, this picture is not mine. That's part of the logo of this program. And it was put together by colleagues and friends, Antonio Leitão and Hoffman, and Baumeister. So this is a group of people that have been working on this for quite a while. So I'm standing on the shoulders of giants, to paraphrase some friends. Okay, so what are we talking about? So we have basically some A, which depends on X, the parameter. And this is going to hopefully give you some Y. And this Y is going to be tainted by noise. Usually this noise is going to be something that refers to uncertainty in the measurements, but also may refer to uncertainty related to the model that we are talking about. And so in my notation over there, the parameters is refer to X, the data refers to Y, and we are trying to invert this and eventually compute from that some quantity of interest. I put on purpose here A applied to X, not necessarily a linear model, yet most of the things that people understand well refer to linear models. And nonlinear models are really a topic of great interest. In fact, my talk today is about nonlinear models. And why don't I give 2 examples, perhaps 3, on inverse problems that are really relevant and don't come from finance, since I think the topic of this conference, although it's mathematical finance, it became also very fashionable to talk about non-mathematical finance subjects. So let me talk about 2 that are close to my heart. One of them is computerized tomography. So what is computerized tomography all about? It's basically imaging without invading, so non-invasive imaging of the interior of bodies, such as, for example, the brain. And here I show you some CT scans of the human brain. In the particular case of tomography, what one has is a body. You send images, you send radiation. Somehow this radiation goes to the body. It gets absorbed, and you try to determine the absorption curve by means of measurements. Now, one thing that you certainly have to notice is that in such a type of procedure, your data is going to be noisy, your data is going to be discrete, and if you try to interpolate your data, you may run into serious troubles. And try to do interpolation in this very linear problem, and you'll see what happens. Also, let me mention that in the very first attempts, when people started writing theoretical models for inversion, one of the things they tried is to produce data and then immediately try to invert from the model. Such process of producing data and with the very same mathematical model, invert, is called the inverse crime. And this is something that one has to avoid as any other criminal activity. So another, a little bit more complicated model that I've worked on and I'm very interested in is related to the so-called diffuse tomography model. In the diffuse tomography model, what happens is that radiation can go anywhere. And a few years ago, again, standing on the shoulders of giants, we looked into a model where we discretize everything, and we talked about random walks on a grid. Such random walk on a grid was made by a certain set of rules, which was basically a two-step Markov process. And this actually was lots of fun. It was a fantastic group. It led to a very interesting paper. Well, interesting in the sense that I had interesting collaboration, not that the paper is interesting per se. It's actually fun. This was published in Science back in '92 with my former PhD advisor and quite a number of interesting people. One of the things we learned in this is that discretized models, even in a very simple context, can take you a long way. And the difficulties, sometimes from the theoretical to the practical, are immense. In particular, one of the things that kills you, even if you have very, very clear computational formulas, is condition numbers. So condition numbers, even for nonlinear models, which you can iteratively try to retrieve back parameters, can kill you and cause a lot of trouble. Also, this model was so much fun that when I listened to Bruno's opening talk, or first talk, that one of the first talks that we had this conference, I remember that I also was playing with neural networks back then. And in fact, the very last paragraph of the paper refers to neural networks. So thanks God I had the memory that we had written that in the paper. And this model is so difficult that it was connected to a neural network. So two things we learned from here is that you have to impose some further information in order to solve inverse problems correctly, in order to regularize. You have to avoid the inverse crime, and you have to deal with the discrete world. And a fourth thing that I didn't mention so far is that many times optimization is hidden in many different processes, in particular in backscattering process, backpropagation process, and all the like. Okay? Yes, sir?
You didn't quite tell us why the inverse crime is a crime.
It's a very simple thing. Take, for example, a 2x2 equation. I'm not going to write the specific numbers, but I'm sure you can figure out. A12y equals b1, a21x plus b, a22y equals b2. Suppose these guys, a1, a2, a21, are related to planes or lines that are very close to parallel. Now, you go ahead and you compute this with your forward model. You believe this is a good model, so you have A1, the A's, A11, A12, etc., well behaved. You put the data, and then with this very same model, now you say, oh, now I have a good model. Let me invert this. Okay, you do that very happily. You go ahead and say, oh, now I have a problem, a way to solve, for example, the tomography problem that I was talking about, except that in that problem, instead of 2x2, you had 1,000,000 by 1,000,000 equations. Well, what happens is that the very moment that you put an epsilon here, your solution goes to hell. And The crime is in the fact that you are using exactly the very same model to produce the data and to invert. And sometimes, even if you don't, you get good results if you add noise here, but you still keep these coefficients, you might get good results provided you use everything else the same. Yet, the moment you now change these coefficients a little bit, then your inverse solution also goes to hell. So that's my point. Okay, so with those things and those ideas said, I'd like to discuss with you a little bit the problem that actually brings you here, which is a math finance problem. After all, we are doing math finance here, or some of us. So I'm going to discuss a continuation of a very interesting subject that in a certain sense was started by Bruno Dupier when he looked into the local volatility models. And I must mention that there was a very interesting mini course that's online by Julien Guillon. So lots of things were said, and he actually gave a very good algorithm to attack such problem. What we are doing here is trying to show that there are other avenues in order to attack such problems. So, stochastic volatility model, local volatility model. It basically tries to put together the features from stochastic volatilities, such as Heston models and the like, and the local volatility, which is extremely powerful in order to fit the smile curve. So the underlying price, S, satisfies some kind of Ito process, with R and D being the usual interest rates, dividend rate. We have the volatility here, which is measuring square of the variance, which is a stochastic variable itself, and satisfies some kind of, let's say, Orsten-Uhlenbeck type process. And there is a correlation between the two Brownian motions, and this is given by rho. Okay? So, well, as I said, this is related to the Heston model. If L is equal to 1, then we are basically back to the traditional stochastic Heston model. Yet, if, on the other hand, you didn't have this process here, you would be basically working with the local volatility model, which is very fond to our heart. I should say, this is joint work with Yuri Saporito and Shu Yang, which I mentioned before. And I'll try to be a little bit faster now. I've spent some good amount of time on my introduction. So, oh, by the way, there is a name for L. It's called the leverage function. And the idea here is really try to calibrate as best as possible the implied volatility surface. So this, the first observation, which is actually a very interesting result by Young back in '86, but it's in a much more general setting, which tells us that this local volatility square at time t and s is actually given by this expected value, given that you are at a certain price s. And since L is S measurable, so you get it out. And so basically, you have a way of relating the local volatility square with the expected value of this variance coming from the model. We are going to define this expected value sigma at Ts. Okay, so this is this expected value. So V of t is in a certain sense the instantaneous variance of the process. Well, but then you can actually look at the full equation for the Fokker-Planck equation for the whole process that I had in the very beginning, this process that we have here. And you can actually observe that this is given by such a ratio of integrals, basically the moment of v with respect to distribution, the expected value of v with respect to distribution divided by the probability measure. The P here satisfies the Fokker-Planck equation, which I just mentioned. Note that the sign here is with minus, so it's in the right way according to the flow of time, and with some kind of initial condition that's usually given by a delta at S0 and V0. Okay? Well, there's the importance, there's a connection between what's happening at the level of volatility and the level of the prices, and this is given by this mixing fraction that we call rho and lambda, so it just a parameter that's called mixing fraction that plays some role in the practical application. I'm not going to go very much into that. So there are different methods to solve the Fokker-Planck equation. In this proposal that we have, this method that we have, we actually are going to use Douglas' scheme, and there is an issue about zero flux, or there is an issue about boundary conditions so that you actually get a good probability distribution. And so we mentioned, for those that are interested, the work Look 2012. Okay? We are going to use the ADI method to solve the Fokker-Planck equation. Classical methods usually they approximate the solution of P only on Tn minus 1, and they evolve with that. We are going to actually consider adjoint methods to solve that equation. Okay? We are going to put some kind of regularized boundary initial condition. Actually, this regularization here is part of the game in this process. But it's something that the PD by itself takes care of. Okay, and now how do we handle the local volatility? Well, actually the motivation for this work was the fact that for many years, myself together with former students, we have been looking at the local volatility. And in fact, the local volatility has and leads to a very interesting problem. From the numerical point of view, from the actual theoretical point of view, we have been using regularization techniques to handle these problems. And the basic tool that we use is actually Dupier's equation, where we have a way of writing the price of, say, calls or puts in terms of the solution to the equation that I have written here. And now we have T as the final time, K as the strike price, and one solves that equation. And I don't really have time to go into the results that we have. But basically, coming back here to the general picture, we now in the notation of local volatility, we have been looking at a map, A, which is the result of taking our A, which I'm going to call X. X now is going to be little a, something like 1/2 of sigma square of the two parameters, and maps that into the prices of calls, let's say, or puts for different strikes and times, okay? And we don't see all the prices. We actually have a projection process here. And we are trying to invert that. So there is another way of looking at the problem that I'm talking about, which I started liking very much. Basically, we have L of A being the variance of our problem, and we solve some kind of PDE, let's say U. So, and then we take the solution of this PDE, so we solve this equals 0, and we take u at different points, let's say tj, kj, j from 1 to n, okay? The first question that we addressed a long time ago is the well-posedness of this problem, which is obviously ill-posed. In fact, I must mention that this issue has been addressed by many people. Particularly, I'm happy that Stefan Capet is on the first row here. This was addressed also in his thesis. Actually, many of these things we learned from his seminal paper at the SIAM, I think it was numerical analysis. Am I right? Okay, yeah. And so what we then address is how to regularize this in a not necessarily quadratic way. And by regularizing, I mean what is necessary to put as a priori information so that you can reconstruct in a stable way your variance or your local volatility based on option prices, okay? And that's what I mean by regularization. So basically what we did is we introduced some functional, let's say f of a, which is, let's say, 1/2 or some norm of my u, a function of a, minus the observed prices, let's say my data, let's call this d square, plus some function f of a, which incorporates in my model the a priori information. And we put here a regularization parameter. And the basic question that one has to address is what can you say when you look at beta as a function of delta, where delta is the noise, because your data is not going to be perfect data. It's not going to be the data that Mateus wanted me to use. This data being corrupted by noise. The only way I can solve this problem, the specific problem I'm talking about, is actually by means of regularization. And so there are questions such as convergence rates, what kind of information you have here. In particular, let me say that this is especially for people in statistics. The formulation that I have in optimization, I can not say any word about optimization, and instead of that, talk about Bayesian inference and say, okay, this f of a in a certain sense is related to some exponential measure, and exponential in the sense of statistics, in the sense of, in particular, if it's quadratic, we are talking about Gaussian noise, but it doesn't need to be Gaussian noise, and we're actually doing some kind of Bayesian inference, okay? So you can say, oh, I'm not doing optimization, I'm doing Bayesian inference. But that's just a question of words. So, as I said, there's lots of people who have worked on this. For example, Marco Avejaneda and Capet. Well, the list goes on, and I apologize if I don't quote anyone here, but the slide is too short for the proof that I have to make. Okay. All right, so we have developed work with in different directions. In particular, one issue that I'd like to address and mention to this audience is something that I learned from my very good friend, Uriashi, collaborator, where he kept saying to us, always respect the sanctity of data. So be very careful when people try to interpolate things. Interpolation may lead to problems. And if you try to do interpolation in either of the two first inverse problems that I mentioned to you, you run into serious trouble, believe me. Okay, so how do we proceed then for this specific method? As I said to you, this local volatility is actually the result of, is related to my leverage function. And basically, we use the information from the regularized local volatility in order to recover the leverage function. Okay? So, in order to compare, we basically compare it with a benchmark model, a benchmark model that was put forward in this reference that I mentioned here. We did not have the opportunity to compare our methods with the very nice methods that Julien Guillon described in his mini course. But I think that this is something that deserves further attention, but requires not only a lot of data, which is very hard for us to get without some further collaborations, but also more manpower. And yet, what we try to do is perhaps look at it from an alternative way. So basically, the benchmark method consists in trying to solve for this leverage function by integrating the p's and the expected value of the variance. And this is basically done by looking at some initialization and then evolving. Again, they start with some initial conditions, like if there was a particle here at this point, S0 and V0, and you would look at the probability of this path in this enlarged space of price and volatility. So assuming we have compute, let's say, the leverage function at time tn, we use a numerical method, we meaning they, but that's the benchmark method, to solve the Fokker-Planck from Tn to Tn plus 1. And from there, one finds the approximation for Ptn plus 1. And you then compute by some kind of averaging the leverage function at the time n plus 1. So it's basically an evolution equation on this benchmark. Note that one of the difficulties, and I didn't mention this especially for non-specialists, is that to solve the Pn plus 1, you somehow need to know this Bn, Ln. So to go from n to n plus 1, you need to know that. That's why this problem becomes hard. In terms of algorithm, what one does is you set the initial condition P0 ij, those regularized probabilities. Then you go ahead and from n equals 0 to n plus 1, you keep solving. Bruno, I understand you have to take an airplane. Thank you very much for being here.
To make sure I would have the beginning. So
okay. Thank you. Thank you for your presence here, Bruno. Okay. So, as I was saying, so you set the initial conditions, you then evolve according to the Fokker-Planck equation, and you update the equation, and then you return the leverage function from 0 to the final time and for all the price values. Okay? What we're going to do is a variation on that theme, but with a little bit more care in order to make sure that we are solving a well-posed problem at each step. Although by well-posed I mean here a regularized problem that originally was ill-posed, but now becomes well-posed when you regularize it. And as I said, we have extensively studied the ill-posedness and the convergence issues connected to the computation of this local volatility. So we use those things that we learned from the previous method, in previous problem, in order to attack this problem. As I said, we are going to use some kind of optimization. which can be disguised in many ways. You can disguise the optimization in, for example, some iterative method. And talking about iterative method, one way of solving this regularized problem that I just mentioned is to go ahead and produce a series of iterates, which are the ones of the, for example, Landweber method. And instead of using this regularization parameter, you select appropriately by some well-known techniques from inverse problems, and also I'm sure people in statistics know about them. You select a stopping rule for your process, okay? So in any case, there is a good amount of work that has been done in the selection of this alpha, the regularizing parameter that we are talking about, and also the regularizing function that one considers here. For example, it's not clear that the noise is really, the a priori noise is Gaussian. There is no reason for that. And because there is no reason for that, there is no reason also for using quadratic optimization here. Okay? Anyway, what else should I say here? Okay, yeah, this is the observation about the different norms. So basically, we are going to work forward with this leverage function. We are going to compute the density in a way that we go from Tn to Tn plus 1 with this initial condition. We are going to, again, denote this approximation by Pn plus 1. What we are going to do is consider, and I'm going to have to introduce a little bit of notation. I know it's very late to go into such things. Just one thing, how much more time do I have?
5 minutes.
5 minutes, okay. I think I can make it in 5 plus epsilon. Regularized epsilon. So we introduce an operator, G1, that sends these leverage functions for all the steps into the next iteration. We initialize this in a natural way. I'll discuss that very soon. From there, we compute this local variance by using this expected value, again by using now this kind of estimation. And the next step is basically to introduce an operator which computes this minimization, the argmin, of these different quantities for the leverage function. And we make sure that in our process we choose in a judicious way the regularization parameters alpha 1 and alpha 2. The choice of all those parameters are based on some kind of natural evaluation. You can use, for example, normal methods of inverse problems there. And so the final algorithm, the one that we propose, is try to solve this minimization problem. So the main difference is the step 3 and 4 that I show here, where we do a minimization with the regularization so that the leverage function is regularized at each level. And then from there, we compute the difference, the next step. By the way, we are assuming that we have already solved the local volatility problem, and again, by means of a suitable solution of the inverse problem. So let me show you some numeric examples. We do, for example, an exercise with domestic and foreign interest rates. We take as variables time, log moneyness, and volatility with lower bounds. This is purely numerical. And then we look at time to maturity of these things. We introduce this. This is a simulated example. Then I'm going to use real data. But first we do some examples with simulated data. we introduced the local variance with, the sigma local, the local volatility, according to this formula. In order to avoid the inverse problem, or inverse crime, I'm sorry, we sample the data on a coarser mesh with, we can solve, for example, the forward problem in one method and use sampling in a coarser mesh. And so this is the ground truth for our leverage function. By ground truth, I'm simulating here. I'm doing just an example. So this is the type of ground leverage function. And this is what we obtain in the presence of noise with the regularized method. So of course, as any good inverse problem, you don't get something that's precisely the same. But we get something that is close to that. The parameters that we chose for the stochastic volatility part of the model are here. And the regularization parameters are chosen based on the L-curve method from inverse problem theory. And so what I'm going to show now is the recovered leverage function and the local volatility surface. And again, as I said, once we estimate, I'm going to read it because it's very important, the leverage function, we can recover the local volatility using the alternating direction implicit method for the Fokker-Planck equation. So this is a comparison of the benchmark method and our proposed method. And what we see here is that away from the at the money, you see a bad behavior. And this is very, very good as compared to that. Okay? Here is a snapshot of that for 0.1 years, so it's about 1 month, a little bit more than 1 month. And in this black starred line, we see the ground truth. For the method we propose, we have our result. For the benchmark method, we have this outer curve. So you see that for further away, out of the money and in the money prices, what we get is something that diverges from the benchmark, from the method that we have, and further away from the ground truth. This is for the half a year, more or less. So you see the oscillations. And what you see here again is that the benchmark method is further away. And this was typical. I didn't select, or we didn't select this as one single example. It's just that this is a typical behavior. For about 10 months, we have a better, a little bit less divergence, but still there is a divergence. So this is, again, the comparison between our proposed method and the benchmark method. Now, how about, okay, this is for shorter periods. For shorter periods, 0.1 year, we have this. So this is, again, another example. I'm going to go a bit faster on that, but you see the same kind of effect that I mentioned before. And now, how about a real data example from FX options using Euro US dollar, March 18, 2015. The spot value was about 1.08, good old days. And so you have here the different options, the option prices. So we plotted here just to remind you, 1 week, 1 month, 1 year, etc. So those are the parameters that we calibrated from the real data. And so this is the estimated local volatility surface. And from the benchmark method, we get this. From the proposed method, we get this. They are not very far, but they show a few differences. Of course, here we don't have the ground truth to compare. Again, our method, away from the main at the money, we have differences that are substantial. And so this is yet another example with real data. And here I call your attention to the fact that the benchmark method is leading to very, very different results away from the add the money at time to maturity. Those are the places where the probabilities are very small, okay? And so this is, again, what we see in this data. And so we actually have analyzed the residuals for both methods. And so I'd like to conclude by mentioning that we feel that our method is more robust to noise. It's more resilient to instabilities in these regions of low probability. It does not require ad hoc procedures to avoid instabilities in these low probability regions. I was going to say religions, but I meant regions. And it respects the data in the sense that we don't use any kind of interpolation to deal with the data. In fact, we have a full paper about this issue of interpolation, and we strongly suggest that interpolation for the solution of such inverse problems is not a good idea. And actually, I would like to refer you to a talk that Uri Asher gave about this, not only for the problem of math finance, but general methods in imaging. So I'd like to finish by saying that these are our collaborators: Vinicius Albani, who is sitting somewhere hidden there; Adriano De Cesaro, who is back in his home; Ottmar Scherzer, whom some of you may know; Shu Yang, Uri Asher, and Yuri. Thank you very much for your attention.